Hello! So for this lecture, I am expecting you to have already gone through this week's tutorial where I walk you through performing a key exchange on an elliptic curve. I wanted to talk about why it is that elliptic curve cryptography uses coordinates from modular arithmetic instead of the real numbers. And then I want to focus a little bit on what is the algebra involved that guarantees that both parties in the key exchange end up with the same secret at the end of the exchange. So part one of this is just going to be talking about why it is we use coordinates in Z mod PZ. And this was something that we've previously talked about when I introduced the ordinary Diffie-Hellman key exchange a couple weeks ago. I think we were still meeting in person at that point. So we talked about the discrete logarithm property. So remember that the Diffie-Hellman key exchange based on exponents mod n, we said that we're going to pick some secret exponent. Here I've used lowercase n as the value of my secret exponent. And in the process of performing the key exchange, we would have some generator that both parties agree on. Here I've just used 2 to make things a bit more explicit. And the question is, can we publish the exact value of 2 to the power n without giving away what n actually is? And it all depends on what system of algebra you're using to make this calculation. So in the real numbers, there's no chance. If you tell somebody that you have got some power of 2, let's say 128, well, they can just go home to their calculator, punch in what's log 2 of 128, and they'd get 7 out of that. So the problem with working in the real numbers in this context is the logarithm is a very easy function to calculate, right? You can just take a Taylor series expansion, you can get as close as you need to, and then figure out what your secret is. And that's not so great for establishing key exchange. The way that we resolved this, or rather the way that Diffie and Hellman resolved this, is to work over the integers mod p instead. So the reason why you can do Taylor series and make a logarithm to be very easy to calculate is that in the real numbers, the logarithm function is increasing. The real numbers are this nice continuous domain, and so you can make those kinds of approximations and get your calculations as close as you need to be. Working in the integers mod p, we've seen before in this class how the multiplication table sort of wraps around on itself, right? Every time we get up to an integer larger than p, we reduce that to one of the residues that are less than p. And because taking higher and higher powers bounces us around the system of residues so many times, the logarithm is a lot harder to calculate in that setting. So that was what made Diffie-Hellman key exchange a safe thing to do back when we were just looking at exponents mod p. So this idea also happens in other kinds of groups, right? So integers mod p is just one kind of group amongst many. And the big takeaway for this part of the lecture is that the elliptic curve groups also have this property. We have some kind of operation that's easy to do in one direction and hard to do in the other direction. So in an arbitrary group, We talk about having multiplication. We say that taking the same element and multiplying it against itself a bunch of times is going to give us an exponent, and that taking the logarithm of that would undo that operation. And in discrete groups, so groups that are based on modular arithmetic, it's generally a thing that the logarithm is hard, while exponents are easy. So people will call this the discrete logarithm problem. They'll say, oh, can you solve the discrete log problem in this group? Yes or no. If it can be solved, then we're not looking at a great system for encryption. So this, like I said, is also a property of the elliptic curve groups. So you would say that the elliptic curve group has a hard discrete logarithm problem. The name is a little bit funny, right? We use the word logarithm here because this idea really does come from the point of view of exponents and logarithms. And it is a thing where we can take repeated addition of points on an elliptic curve, and that's a relatively easy calculation to make. And then the result, the opposite of that, right, the division, will be much harder to do. So we still call it the discrete logarithm problem just because that's the notation. But the idea is if you have some secret integer n, and you have a point P that's on the curve, you can calculate the coordinates of n times P very easily. So remember, this is n copies of the point P added together according to the point addition formula on an elliptic curve. But if an attacker knows the point P that we started at, and knows the point n times P that we've published in order to do the key exchange, calculating that original n is going to be very slow, right? It's not impossible. The attacker will be able to calculate it eventually, but the security for this kind of exchange comes by estimating the amount of time that an attacker would need to invest in attacking this discrete log problem, and just stacking the deck so that it'll take something absurd, like 100,000 years or something like that. So one of the reasons that we use coordinates from z mod pz when we're working in elliptic curves, yes, it makes the picture a little bit less intuitive, but it gives us this nice setting where we can easily calculate n times p, and attackers have a difficult time of recovering that original n. There is another reason why we would bother with this kind of setup, and that's that elliptic curve cryptography is generally considered to be quantum safe. So this is a term that you'll see get thrown around a lot if you work in cryptography. The problem is this. So we've had the good old Diffie-Hellman key exchange using exponentiation for a number of decades now. And we've had RSA encryption, right, using two different primes and encrypting our messages in the multiplication group there, right? We've had both of those things for a while. And the problem is the quantum factorization algorithm. I'm not going to go a whole lot into the details. This is not really a course on algorithms or in computer science, and I'm not a computer scientist. I don't have the knowledge to really explain what's going on there. The facts of the matter that we need for right now is that there is an algorithm that people already know called the quantum factorization algorithm. And what it can do is it can factor integers much faster than any algorithm on a traditional computer. And what that allows an attacker to do is that an attacker who's able to run the quantum factorization algorithm can actually break RSA encryption much faster than they would by the ordinary, just give it off to a server farm and wait 100,000 years. So this is something that's a problem for encryption systems that are based on exponents, like we worked with a couple months ago. There is a catch. The first catch is that we don't yet have quantum computers that are big enough to actually run the algorithm. So we know what all the steps of the algorithm would be, and they are steps that you need a quantum computer to make, and not just an ordinary, traditional computer. But at this point, the actual hardware is still experimental. I think a couple years ago, there was a successful demonstration where they got 2 quantum bits talking to each other and were able to factor the integer 15, I believe it was. So still very experimental, at least if you go off of what's been disclosed to the public, but that's another story. Right now, we don't think that anybody has a secret quantum computer that can just destroy encryption as we know it. The other catch is that the quantum factorization algorithm is only really a leg up on RSA. This algorithm does not let attackers solve the discrete logarithm problem in other kinds of groups, particularly in the elliptic curve groups that we have been building up in the past couple weeks. So one of the reasons I wanted to make sure that we get exposure to elliptic curves in this class is that elliptic curve cryptography is considered to be like one of the major avenues for developing quantum safe cryptography, right? So in the future, if there are widespread quantum computers, RSA is not going to be good enough to keep a secret anymore. One of the places that researchers are trying to build up new kinds of cryptography are using these elliptic curves. So that's an ongoing part of research right now. If you look up things like what are, say, web standards for signing web server certificates, most of those are now switching over to elliptic curve methods in place of the older RSA stuff. Now, elliptic curves aren't the only way that you can try to build quantum safe cryptography. They're just sort of the biggest way, or the most studied way. I don't want to get us bogged down with too much other groups and other algebraic ideas. It's a vast world out there, and this is just sort of like the big one that you should at least know the name of and have an idea of what people are talking about. So in part 2 of this lecture, I want to walk through the actual algebra that's going on behind the scenes as to why 2 different people can jointly come up with the same secret coordinates. I'll see you in a bit.